is Tim Brailsford. I'm from the University of Nottingham. You may well be aware of the fact that we have a collaboration arrangement, a twinning deal with Binus University, which has various interesting opportunities that I'll be talking to you about this afternoon. But University of Nottingham, you should know, is a very large British university. We're a very good university. Recently we've been promoted to number 70 in the world, and that's not bad because there are a lot of universities in the world. But we're very big, and we're big enough to have multiple campuses in multiple countries. We've got a campus in China and a campus in Malaysia. And I'm from Nottingham. I've been in Nottingham in the UK in many years. I've been on our Malaysia campus for the last 5 years. But I'm here representing the whole of the University of Nottingham, so not just talking about Malaysia campus. Now, I don't want this to be a boring careers talk, so I'm actually going to do 2 talks today, so I need to move reasonably swiftly because I apologise, I've got to leave to go and get on a plane very shortly. But first of all, that's actually the second talk. The second talk is going to be about Nottingham and about studying computer science in Nottingham and about opportunities that will be available to you. The first talk, though, is something which is more of a general interest talk that I hope will be of interest to people who are studying computers and studying computer science, because a lot of students don't actually give much thought to where all this stuff comes from. This is a little bit of history, but it's also a little bit of theory about actually what are these computer things. And I've called this From Maths to Apps and Games, and what I'm trying to do in the next half hour, so I apologise if I skip a few bits, what I'm going to try and do is give you an idea of how, from very much the world of theory and maths, and modern world of smartphones and what have you has come. Because if we... Where's my zapper working? It was being wildly temperamental earlier on. It may not be... Okay. Oh, it is working, yeah. I don't know if you've got some sort of ultra-thick walls or something here in Venus. Ever since I got here, I've had problems with this thing. Anyway, never mind. Just think for a moment. You're all familiar with the world of smartphones and apps. Just think about those devices for a moment. They're extraordinary devices. You use them for a lot of things. What do you mostly use your smartphones for? Well, probably mostly staying in touch with your friends. And for social media and Facebook and Twitter and Line and texting and all that sort of stuff. But I'm sure you also use them for looking things up and as information resources, and you quite possibly use them for navigating around the world using Google Maps and Waze and things like that, and maybe you even occasionally make phone calls with them. They are, after all, still phones. But they're a lot more than phones. They're an awful lot more than phones. They are very general, very generic information appliances. And the extraordinary thing, though, is that they are phones. They're mobile phones. And if you ask somebody for a mobile phone 100 years ago, you've got something like this. This is a 100-year-old military mobile phone. And it most certainly wasn't wireless. And it's a very interesting question of how did we, in 100 years, which in the in an old length of human history is nothing really, how did we in 100 years come from this world of mobile phones to your smartphone? That is a very interesting story, and in a very abbreviated way. That's what I'm going to be trying to tell today. So That's a smartphone. We may be a bit washed out in some of these images, but never mind. We start off this story very firmly in the world of maths, the world of very, very theoretical maths. And I'm actually going to start off by talking about this person, Alan Turing. How many of you have heard of Alan Turing? Put your hands up if you heard of Alan Turing. Several of you. How many of it was because of the big Hollywood movie last year? There was, of course, this big movie about Alan Turing, which is fantastic because Alan Turing was one of the great minds of the 20th century. He is one of the greatest scientists of all time, without a doubt. And without his vision and his insight, we wouldn't have our world. I mean, we wouldn't have computers. We wouldn't have any of the technology that you are studying. So it's very interesting to think what he actually did. He was a mathematician. And he was an unusual mathematician because he was a mathematician who was interested in people. And he was interested in studying people's behaviour and trying to formulate human behaviour and actually come up with mathematical descriptions of things that people did. And one of the things that he was particularly interested in what people did was how people made calculations, how people did maths. He was a mathematician. He was a mathematician. He was interested in how people went about doing maths. Now this brings us on to something that's very interesting. How many of you know where the word computer came from? Would anybody like to have a guess? Where did the word computer come from? What does the word computer originally mean? Anybody know? Any ideas? Sorry, somebody have an idea? Yeah, I don't mean the area it came from, or language. No, I mean, what does it mean? What does the word computer mean? Because it doesn't mean what it means today. I can assure you of that. And you can find references to the word computer in literature 200 years old. The word computer predates these things. It predates electronics. And originally, the word computer, sorry, what is computing? I'm skipping things a bit, but the word computer was a job description. A computer is a person who computes. Because, think about this for a moment, maths needed doing long before there were computers. Hundreds of years ago, there were banks, and those banks calculated interest rates on loans. Thousands of years ago, people were building bridges, and engineers needed to do calculations to keep those bridges up. Well, how was that done in the days before there were all these electronic devices? Well, you had, this is the thing, this is a 19th century bank. This is what banks looked like 150 years ago. You see, there were long rows of people sitting doing calculations with lots and lots of paper and lots of pencils. And these people are computers. I remember once reading in a book that was written in this sort of time, the statement, these days many computers are women. Which, until you realise that it's a job description, is a bit of a peculiar statement to modern audiences. But these were the computers that Alan Turing was interested in. He was interested in how the people compute. So let's think for a moment, without using electronics, how do people compute? I'm going to start off with rocks. And I have here some rocks. Basic computation devices. If you take 2 rocks and add another 3 rocks, we have 5 rocks. We take one away and we have 4 rocks. Now this might sound ridiculously trivial, but actually it's quite profound. And what we're doing here is we are doing computation in the sense that those guys would recognise with physical things, rocks. And this is the oldest, I mean, without a doubt, the oldest computation device in the world. But just think for a moment, from the perspective of a merchant thousands of years ago. You're trying to keep track of your stock and your prices. That's probably a pretty good way of doing it. It's a lot better than trying to keep it all in your head. And that is a computing device. Now, physical things can represent numbers. That's what we're doing there. And by moving them around, we can start doing maths. Now, of course, it's not a very big leap from this. From the rocks on beat on strings, and we've got an abacus. And I do approximately know how to use one of these things. I'm probably not going to now because I can use it very slowly and it will take time. But if you've ever seen somebody who is proficient using an abacus, it's a very simple device. You start over here, and these beads represent ones, 1, 2, 3, 4, 5. We can then push that down, and that one up there represents 5. These represent tens, these represent hundreds, these represent thousands. And you can do calculations of big numbers. And you can, if you know the rules of exchanging the beads on the columns, you can do a lot more than just addition and subtraction. You can do multiplication, you can do division, you can do sophisticated stuff. People who are practiced at abacuses can do it very fast. They are a computation tool. We're doing computation with physical objects. Now, this is the stuff that was interesting Alan Turing, because he was fascinated by the idea of doing computation with physical objects. And he wasn't the first person to think of this. Going back further, you had these two people, wonderful, wonderful people, very important in the history of all of this. On the right here, we have a gentleman who lived in the first half of the 19th century, called Charles Babbage, and he was a mathematician and an engineer, and he designed an extraordinary machine. It's like a giant abacus, and this actually is a modern recreation of it in the Science Museum in London. But it is a massive computing device. It's hand-cranked. You turn your handle, and I've seen it in operation. It's cranked up twice a day. It's an amazing device to see. And it does really complicated computation. He wanted to use it to calculate things like navigation tables for ships, which are really complicated maths and were massively expensive to calculate by hand and subject to mistakes. He unfortunately never got the funding to build this machine. He designed it, but as far as he was concerned, it was always a theoretical machine. It would have been incredibly expensive to build in those days because of the precision engineering that would have been needed. This, like I say, was a London Science Museum project to actually build Babbage's machine, and they did, and it worked perfectly from his plans. But he also was very good friends with this lady here, who was an extraordinary person. She is one of my great heroes out of the history of science. Her name is Ada Lovelace. And Ada Lovelace was a British countess in the first part of the 19th century. Very interesting character. The daughter, a proper British aristocrat, the daughter of Lord Byron, one of the most famous poets in the whole English language. And she was also a very, very good mathematician. I mean, when I say very good, probably the best mathematician in her day, which was incredibly unusual for a woman in the 1840s. Women didn't do that sort of thing. Well, this one did. And she worked with Babbage. She wrote what we now call computer programs. This is the world's first programmer. And not only did she invent the concept of a program that could be run in a device, but she even realized that it's quite easy to put mistakes into them, and she developed protocols for debugging her software. She really was the world's first programmer and did an almighty amount with this for these machines that sadly were never built, and therefore her programs were never run, which was a real shame. Okay, this is all the where Alan Turing was coming from. But the big limitation of these machines is they're dedicated to one thing. They're dedicated to doing one job, to calculating a certain type of problem. You can change the parameters, you can run AGI analysis programs. The AGI analysis programs would need to actually be kind of built into the machines. This sort of machine was built later on, and this is a much smaller version of the previous thing, which is a mechanical calculating machine. Now these things were used a lot in the late 19th and early 20th centuries. You sometimes see them in old booths. In fact, they were still in use right up until the 1950s, 1960s, because although there were electronic computers then, the electronic computers are really expensive. So if you couldn't afford the vast sums of money that an electronic computer had, you could still have these hand-cranked machines, and they could do basic calculations. This one was a sophisticated one. You see, it even has a printer attached with a typewriter ribbon and what have you. Entirely mechanical, no electronics whatsoever. You crank the thing up. I've been lucky enough to play with them when I was at school. Although I'm not quite old enough that we actually had them to seriously use. But I was at the sort of school that had been around for a while, and we still had these things in cupboards from the days when they did seriously use them, and we every now and again got them out and played with them. Do your calculations and get fit at the same time. Quite hard work. But anyhow, this brings us back to Alan Turing. He was very interested in this idea of how do you calculate, how do you compute, how do you do stuff. And he is a serious mathematician. And he, in 1936, wrote a paper. I'm afraid it's horribly washed out, so you can't really see it. But he wrote a paper that was called On Computable Numbers. And it was lots of... you also can't see that, I'm afraid. Sorry about that. But it was lots of heavy-duty maths. And basically, the theory in this paper is that any problem in maths, and mathematicians would argue that any problems at all can be expressed in maths, so by extension any problem can be solved if you break it up into small enough parts. That essentially was his mathematical theory in this paper. But to demonstrate this theory, he created a hypothetical machine. He can build it. He was a mathematician. It's all very theoretical. And the bit you really can't read here is about his machine. And he created a hypothetical machine that by following some very, very simple instructions could actually do anything, could solve any problem. It's what he called universal. And these machines have since become known as Turing machines, I mean, he never called them Turing machines, he wasn't that egotistical. But these are very much the foundation of computers and computing. Now, what I want to do right now, it just says that, that's not that. The key thing is it doesn't just solve any problem, it solves all problems. That's the thing about Turing machines. I want to give you a few examples of some working Turing machines. I'm going to talk you through my first one very, very swiftly without demonstrating it, but let's have some programs up there. You can create a sort of Turing machine out of a toilet roll. Because what a Turing machine consists of is a very long tape. And in fact, in Alan Turing's original design, the tape is infinite. Mathematicians can do things like that. So you have an infinite tape, but actually to be able to solve any problems, you do need an infinite tape, and that is a bit of an issue. Though with modern computers, it's not that far off being infinite. But you need a very long tape, and toilet rolls are good tape. You divide it up into cells, and toilet rolls are nice and neatly divided into cells. And then you basically can do four things with a Turing machine. You can move the tape left, you can move the tape to the right, so you can move it one cell left, one cell right, and you can read what is all written on the tape, and you can write stuff onto the tape. And what I do when I'm not quite so up against time is I've actually got two little programs here, which again I'm afraid are a bit washed out, but these programs, which is what Alan Turing called the transition table, we can execute these with this, and I have over here a marker pen, because that will allow us to write. We have to literally cross things out on the toilet roll, but this program is just going to move the tape along until we hit A1. So at every level we move forward. If it's 0, we jump back to 1. We move forward. Is it 0? Jump back to 1. Jump back to 1. Oh yes, it is 1. Then we fall off the bottom and stop. This is a bit more sophisticated. This is going to take every 0 and turn it into a 1, every 1 and turn it into a 0. But again, it's you see just jumping up and down. These things are amazing to see, and I have some better examples in progress. Now this is a rather more complicated program. This is adding two numbers together. I'm not going to explain how it works, but I am going to show you it in action. Can we turn the lights off a bit?
Yes.
That would help. I'm just going to show you a video of a Turing machine I made that's a little bit more sophisticated than a toilet roll, but not much. It's a Turing machine made out of paper. And you see we've got a tape, you will see the transition table when I start it running, and we're going to execute that program that runs two numbers, that puts two numbers together. So you can see, well, you probably can't read it there, but it says Paper Turing Machine Unary Edition, and what we're doing is we're putting in the initial starting position, which is two numbers. You can probably just about see them, but that is 2 plus 2. That's what we're going to calculate. And now I will speed it up a fair bit so it doesn't take us too long. But up here, you really can't see it very much. If you've got time at the end, come and look at it on my screen. It's quite fun. You can see the transition table, and I'm moving this pink pointer up and down as we get into the bits, and we're jumping around and following things, and reading and writing and following the instructions. And we will, when we've finished, which at this speed will take about 5 seconds more, it's got, I can see from this distance, you probably can't, but 1, 1, which is 2, 1, 1 is 2, and we've now written all of those instructions, 1, 2, 3, 4, which is 4. It's told us 2 plus 2 equals 4. Not a big bit of computation, but it's interesting to see that out of a piece of paper tape and a pencil. If you feel so inclined, anybody can make these things at home. And Alan Turing envisaged these as machines. So they are machines. They are physical machines that you can build. And I have built one. I don't have time to show you the real thing. I hasten to add I didn't design it. But it is possible to build these machines out of Lego. Here is a Lego Turing machine. And like I said, I built one of these, and if I had a bit more time, I would actually show you the real thing. But let's just get an idea of this. You will see we're again going to run exactly that same program. We're putting two numbers together. We've got the tape here, but we're representing ones and zeros, Lego bricks that we can flip one way or another. And they don't have to be ones and zeros. We can use any symbols in a Turing machine, but in modern computers use ones and zeros because they're easy to represent with switches. And we wind it backwards and forwards. We put in some data. So here we're putting in the data that is 2 plus 2. Excuse me. And we are going to do some calculations. So we leave it away. We've got an optical sensor that can read what the state of the tape is at any one position. So we can move the tape with lots of gears and cogs. And there's the reader. He reads it with a green light. And now it can write things onto the tape with this flipper, which will flip them from one state to another. Oh, that's the reader again. We're reading, now we're flipping. And so it writes a 0 to 1 or vice versa. I will just speed this up lots. But it winds backwards and forwards, and it goes through, and the program, it winds up with 2 plus 2 equals 4 at the end, which is good, because otherwise there'll be something wonky with math. So now that was all completely theoretical. Just came back to, excuse me a moment, find the presentations, wrong one. Right, so let's go back to Alan Turing. Now, those of you who've seen the movie will know that Alan Turing speculated in that paper about various things that you could do with this sort of machine. And one of the things that he speculated was you could use it for cryptography, for codes and ciphers. And he then got recruited by an ultra-secret part of the British government during the Second World War to break the supposedly unbreakable German codes, which the entire German communications network was based on this encryption that they were very confident nobody could break. Well, Alan Turing was given the job of breaking it, and so he built his machine. And this is one of the very few pictures of that, the very few photographs of that original machine. You'll have seen a reconstruction in the movie, those who saw the movie, which was, because it was an ultra-secret project, there were never very many photographs of it, and the machine was destroyed as soon as the war was over. So I think this is actually the only photograph of it, but you could, I don't know what the bits are, but nonetheless, it's representing the numbers by physical things and the states by these cylinders that rotate round, and it did successfully break the supposedly unbreakable German encryption codes. Now, that really was the first electronic computer. And after the war, Alan Turing went on and moved to Manchester, went to Manchester University and built this, which was the Manchester Mark I, which really was, it was the first computer that was built outside of military secrecy. And this was getting into being a recognisable computer. This could run software that you would recognise, but still written in the sort of language that you just saw, but nonetheless it's starting to get something more akin to a modern computer. And from that, once you get into the 50s and 60s, computers were still big, they took entire buildings. There's only a very small part of one, but nonetheless they started turning into commercial endeavours rather than, with sort of IBM logo on the top, commercial endeavours rather than very much experimental academic things. And from that there was a process of miniaturisation. By the early 60s you got this is the PDP-11, which was this was one of the very first mini computers, it was so called, because the entire computer was in one cabinet. And then the American space program happened. Now, the American space program drove a lot of technologies, but in computer science was particularly important because it takes an awful lot of calculations to get to the moon. And they very obviously needed a computer, but they really couldn't take along something like that. So they also had the advantage of having effectively infinite money, and so they developed this, this is the computer from the Apollo lander, which is about the size of this abacus. I mean, it's a phenomenal feat of miniaturisation, given what the computers are generally like in these days. And that, of course, spun off into rapidly the world we know. You've got IBM, because IBM were involved in the space program and started and learned how to miniaturise things. And you've got this, which can sit on somebody's desk. And it's not a very big leap from that to the sort of modern computers that you get, kind of recognisable. And from that, of course, you miniaturise even more. Miniaturisation has been hugely important with all of this. Now, people today don't write programs in move forward, move back, move forward, move back, write one. You probably, unless you're interested in Turing machines, which are interesting theoretical things, you've probably never written a program like that. It's an interesting exercise. You maybe should have a go. There are lots of nice little Turing simulators on the web, or you can make your own out of paper. It is an interesting exercise writing a program like that. But what you generally do these days is write programs in what are called programming languages. Now, this is an interesting development which will, again, does strange things to your head if you think about it too much. But computers, according to Alan Turing, can solve any problem. Therefore, they can solve the problem of programming themselves. And so one of the first problems that computers are set to solve was how do you go about programming computers? And what you write computer programming in the modern world is in languages like, here it's, sorry, there's the front of the C textbook, you completely can't see the C, it should be the C programming language. You probably, a lot of you have seen C. C is, you type in the text in a sort of pseudo-English, feed it into a computer program called a compiler, and it will magically make it into something that does stuff. The computer is solving the problems of how to program. And this is the way that people interact with computers for the most part these days. Programming languages don't have to look like that. Programming languages don't have to look like text. There are all sorts of programming languages. This is one I love. It's called Scratch. If you've not come across Scratch, Google it, download it, it's free. Scratch is a wonderful programming language written by some very clever people in MIT to teach children how to program. And it's all about creating cartoon games by snapping these bricks together. It's still programming. You've still got variables and loops and control structures and what have you, but there's no code. You just snap everything together. It's a fabulous. I love Scratch. It's great piece of software. So, that's programming languages. That's really where we are today. That is the last, 90 years of development in a nutshell. The interesting question, really, is where is it all going next? Because what is the future of computer science? And certainly the question that should be foremost in your minds, if you're starting out on careers in these things, is what's it like now? Okay, that's what you've got to learn and pass your exams. But a much more interesting question is what's it going to be like in 10 years' time, or 20 years' time, or as somebody this morning asked me, 50 to 100 years' time. Well, 50 to 100 years' time is interesting. We can have that conversation if you like. I'll think more 5 to 10 years, but I can certainly see some very interesting trends. Oh dear. Sorry, the reason I say that, oh dear, is that should say the disappearing computer. And I've done that in a font that was slightly faded but still legible. I seem to have slight issues with my projecting here, and the disappearing computer has disappeared. But nonetheless, the idea of this is that computers are disappearing. These things, with screens and keyboards and what have you, are already getting rarer than they used to be. What you have now is phones and tablets and stuff like that. But increasingly, what you have is other devices, it's phones, things like that. Often you will have strange user interfaces. You don't use a keyboard necessarily anymore. That's a Nintendo Wii. But again, you can have a user interface that's very physical, very moving about. This is a fabulous piece of technology. They're things called Siftios. They're children's building bricks. That everyone's a little computer with a screen, and it talks to the others, it knows which ones it's next, so you can design touchy-feely games. Computers don't look like computers anymore. And frequently, they are just disappearing into the fabric of the world around us. Everything can be a computer. So when I say computers are disappearing, they're disappearing from view, but they're everywhere. And this is, I don't suppose you can read any of that, but it's quite an interesting graphic that is just showing you all of the various computers that there are in a modern car. There are a lot of computers and computer systems in a car. The brakes are generally controlled by computers. So if you jam your brake on hard, it's actually a computer that will be doing all the pumping action, all the anti-lock stuff. The accelerators of modern cars are not actually attached to the throttle. You press your foot down on the gas pedal, it may feel like a throttle, that's just because there's a spring there to make it feel right. But actually, what you're doing is it's connected to a box of electronics, to a computer, which is controlling the engine. And that's why modern cars are relatively easy to drive. If you try driving a vintage car, a sort of 60, 70-year-old car, most people who've been taught to drive modern cars wouldn't even get to go anywhere. I mean, they were much, much harder to drive because of all the lack of electronics and computerization. And again, I mean, this is a long list here. Even though the airbags are under computer control, attached to various sensors and what have you. And here are just lots of appliances. These are all computers in one way, shape or form. Even the kettle. It is possible to get a kettle on the wireless network that you can turn on remotely. And again, we're going to be getting more and more of these sorts of things in the future. And a really interesting trend, one that we've been doing quite a lot of research on in the University of Nottingham, is what is called the Internet of Things. And the Internet of Things is, I think, going to become really, really important in the next sort of 5 to 10 years. The idea of this is not only can everything be a computer, but that everything can communicate with everything else. If you've got an electronic device, it should, and at some point in the fairly near future, probably will be able to communicate with any other electronic device. You don't even need electronic devices. You can put little and very cheap tags into pretty much any manufactured object. And the vision of the Internet of Things is if something is made in a factory, there's no earthly reason why it can't have an electronic tag and just be part of this vast global network. That is all technically perfectly feasible and is kind of coming. So this is very much where I see computer science going over the next decade or so. It's that computers in these things will gradually disappear, but everything will become a computer, and eventually everything will become a connected computer. Okay, I've got not very much time because I really do need to pile on and talk to you about Nottingham, but very briefly, we've got time for 1 or 2 questions, if anybody wants to ask any questions. And then I have a prize, sadly only one prize, but we will have a quiz to see who gets the prize, and the multiple to see who is awake. But first of all, questions. Anybody got any questions they want to ask? No? Okay, in which case we go on to the second talk and the quiz. And prizes are always good. So, here we go. The quiz. I've got several questions here because I did this for a much bigger group earlier on this morning, but although I had 3 prizes then, there were a lot more of them, so you've got better odds. I'm going to be the judge, and if you know the answer to this, stick your hand up, and the first person that I see, and walk out here and turn around and turn around, the person that I see with a hand up, if they get the right answer, will win the prize. What is the name of the first computer programmer? Yes!
Kind of long place.
Thank you! Come up to the front. Thank you very much. Well done.
No problem.
Okay. It's not a very exciting prize, sorry about that, but anyway.